Hopefully it is visible, is it?
Yes.
Okay.
But can you please your mic in Zoom? Because we hear you 2 times. Mic on.
Pardon? I didn't realize what.
Can you close your mic and Zoom?
Ah, yes, thank you very much for reminding me that. Yes, I will close the microphone here. You will have a little bit of blurry picture of me in Zoom, but that's not good enough to see this, but hopefully it is better now, yes? And then you can chat me here, but I will not be able to see it from far away, okay? So, okay, so yeah, if everything is okay, we can start now. Okay, so today I want to talk about the last part of this chapter, which is very important, and that's called mathematical induction. It's a very powerful tool to prove statements related to, I need to remember to look at this camera, okay. So it would be a very powerful tool if you want to prove statements regarding natural numbers only, okay. So let me start by writing it, and then I will tell you what is the meaning of this. Let me write this. Let P of n be a statement regarding a natural number n. So this is important, such that number 1, P for 1 is true. Yes. And number 2, if Pk for some natural number k if Pk is true, then P of k plus 1 is also true. Then Pn is true for all natural numbers. So this is called the principle. Yes? Yes? No, k should be 1 as well. It doesn't matter. In this case, k can also be 1. Yeah. So what we say is that Pn is a statement regarding the natural number n, yes? And then we know 2 things about this statement Pn. One thing is that the P for the first natural number n equal to 1 is true. And we know something very important. We know that whenever P is true for one value k, one natural value for k, it is also true for the next one. P is also true for k plus 1. If your statement enjoys these 2 properties, you can conclude that your statement is valid for all possible choices of natural numbers n, yes? And I think it's intuitively clear, yes? So for example, you say that, so the first one tells you that n, for n equal to 1, the statement is true. Then this tells you that if a statement is true for at the k level, it can jump to the next level k plus 1. Okay, so in the first step, you just check that P is true for 1. The second one tells you that you can go from step K to step K plus 1. Okay, so in first one, you know that this statement is true for 1. This tells you that if it is true for K, it is true for the next one. We know that this is true for 1, so it means that this is true for 2. Now it means that P2 is true, so it means that the next one should also be true according to the second property again. So it means that because P2 is true, you can go to next one, which is P3. Now P3 is true, you can go to the next step, which means that P4 is also true. Yes? So that's the idea. I hope that the idea is clear. So somehow if you consider a staircase, this tells you that you can go onto the first step, okay? And then it tells you that if you are in any stair, you can go to the next one. Okay, now you are in the first one. Because you can go to the next one, you go to the second one. Now you are in the second one because you are supposed to go to you are able to go to the next one, you go to the third one, and now you're in the third one, you go to the fourth one, and etc., etc. So hopefully this is called mathematical, the principle of mathematical induction. Hopefully the idea behind that this is true. Yes, this part is called the base of induction. Okay, and this part so this is called induction hypothesis. Okay, so these are the names that we usually use them. But let me put them in examples. I think the best way to do this is to do it from the exercise point of view. So, but let me mention that this is only useful if you want to prove something regarding a natural number. That's the only thing that you can do. Okay, and then almost in every parts of mathematics that you have a statement regarding a natural number, a very powerful tool in your hand would be mathematical induction. Let me start with very simple examples. Okay, there are different types of examples. All of them are included in the book, so I want to go through all of them. So example, use mathematical induction to prove the following statements for any natural number n. Okay, so number one. So this is a very famous formula, but let us start from here. 1 plus 2 plus 3 plus up to n, yes? Hopefully you remember the formula for this, of course. But I want to give you the formula and I want to prove it using the mathematical induction. So that's actually a weakness in mathematical induction, because you need to know the right-hand side as well. What you can do is to actually prove it. So it means that the formula in its entirety should be given to you, and then you should, in principle, you are able to use mathematical induction to prove it, okay? So it doesn't have predictive power. Of course, I will talk a little bit about that one as well, but in principle, if I ask you calculate this using mathematical induction, it's not possible in general. So what I need to do, I need to give you the formula in its entirety and then ask you to prove this. Okay, so that is the main weakness of mathematical induction. So you need to have the formula in its entirety. Okay, but what is my point is to learn how to do these steps. So the first thing that we do is this. The first thing is that this statement Pn is this statement. So let me write everything in detail here. I want to prove this. This is a statement regarding the natural number n, yes? So I will call this statement Pn. So my statement Pn is this expression, is this equality. Okay. Of course, in principle, you really don't need to write it. So I just want to follow every step here so that you can understand what's going on. The first step is the base of induction. I need to check if P1 is true or false. Yes. So what is the meaning of P1? So you need to have a good way of reading this formula. This formula tells you that if you give me n, I will start adding the natural numbers from 1 up to n, and then this is claiming that this would be equal to that number multiplied by the next number divided by 2. Now what is happening? I am giving you that n is equal to 1. So it means that you start from 1, you are supposed to continue one after the other until you reach to that number n. But because this number n is equal to 1, when you start 1, you have to stop there because you have already reached to the nth level, because n is 1 in this case. And then you need to put 1 here on the right-hand side and check that if this 1 is true or false. Okay, so this is my statement regarding the natural number n. Now I am checking the validity of this statement for n equal to 1. The left-hand side for n equal to 1 becomes just simply 1. The right-hand side for n equal to 1 becomes this. And I ask myself, is this statement true or false? Which is clearly true, yes? Because the left-hand side is 1. This is true if and only if 1 is equal to 1 plus 1 is 2 times 1 is 2 divided by 2 is 1. So this is true. So P1 is true. Okay, now what should I do? I need to do PK. I need to write PK. This is my assumption as I assume myself that this is valid for some number k. Okay, so for some natural number k. So what does it mean? It means that if you give me k and I add numbers from 1 up to k, it is equal to k plus 1 divided by 2. So this is assumed to be true. Yes, so we assume that this is valid for a k. Now what should I do? I need to check the validity for the next one, k plus 1. Okay, so how should I write pk plus 1? Now I give you k plus 1. So again, you start from 1, the next one is 2, the next one is 3, and then you continue in the same way until you reach to k plus first level. Okay? Okay, but it is clear that when you reach to this level, the previous one is the kth level, yes? And on the right-hand side, you write everywhere you see k, you need to replace it with k plus 1. So instead of k, you have k plus 1. Instead of this k, you plug k plus 1, but there is another 1 there, so it becomes k plus 2, and then divided by 2. Okay. This we need to prove, yes? Based on the assumption. Okay, So, any questions so far? Okay, so it's very, very important that you understand what is going on. I am assuming that this equality is true. Based on the truth of this statement, I want to prove this statement. Okay, so it's a very, very powerful tool, by the way. You see, I am more or less using the same formula itself to prove something about itself. And the point is that this, if you understand, it's not a circular argument, it's a valid way of arguing. This tells me that assuming that this is true for k, what I do, I show that it is possible to go from the kth step to the k plus first step. And this tells you that the first step is true. The first step is true, so it becomes second step is true. Now second step is true, it means that the next one, third step is true, and then it continues. Okay. Now let us see how we can do this problem. Okay, so let me... So let me clean here. Okay, so my goal is to prove this. Okay, so I will start from the left-hand side of what I want to prove and try to use my assumption to reach to the other side. So that is the general strategy in solving these kind of problems. So I will write the left-hand side. What is the left-hand side? Then let me repeat the left-hand side. It is 1 plus 2 plus 3 up to plus k plus 1. Yes? This is the left-hand side of this expression. But now I want to continue. This part, I know what is the value for this part. Because if you see, this step is assumed to be true. So I know that if I add numbers from 1 to k, it becomes k times k plus 1 over 2. So it means that instead of this expression, I can just simply plug k times k plus 1 divided by 2. Okay, so what happens? Instead of this expression, I can just write k times k plus 1 divided by 2. And then after that, I have plus this expression. So I would write plus k plus 1. And now it's not finished yet because I haven't reached exactly to what I want to show. So I need to do some algebra. Okay, by having an I on the right-hand side, you see that I have one single fraction with denominator equal to 2, but I have here two expressions. So this motivates me to have a common denominator, okay? So I can assume that the denominator here is 1. So it means that I can take the common denominator to be 2. So this becomes k times k plus 1, and then you have plus 2 to 1 2 times. I have to multiply it by the numerator. So it becomes 2 times k plus 1. Okay, now immediately you see that k plus 1 appears here and there. So it's a common factor. So I can pull it out, yes? So what happens? It becomes k plus 1. From this one, k is left. Plus 2 is left from the second one, divided by 2. And then if you see, that's exactly the right-hand side of what you're supposed to show. So this becomes the right-hand side. Okay, so this is probably the simplest possible example teaching you the mathematical induction. So I presented a formula regarding the natural number n in its full entirety. By this, I mean that I gave you the left-hand side and the right-hand side, and I want you to prove this equality. Okay, so what you need to understand is that this equality itself is my statement. Okay, now according to mathematical induction, the principle of mathematical induction, what I need to do is to check the truth of this equality for n equal to 1 manually by hand. Okay, I just check it. If it is true, then I assume that this expression is valid for n equal to k for some k value. This means assumed to be true. I myself assume that this equality is true. I want you to understand that this is not a circular argument. You might say that, how should I know that this is true? Because then the only difference between this and that is that I have changed the letter n to letter k, and we know in algebra it doesn't have any significant role in changing them. I want you to understand this is not a circular argument. So what I'm saying is that what I am assuming that this is valid for some value k, and I want to show that this also remains valid for the next number. This is the logic. Nobody tells that this is true. I'm assuming that this is true, and I want to show that the next step is also true. Okay? So, and then because I have this base, it means that I know one is true, and I showed that from each step, I can go to the next step. This is what I am showing here. It's not a circular argument, okay? Okay, so then what I did, I wrote P for K, I wrote my statement for K plus 1. So it means that wherever I see K, I replace it with K plus 1. And then I assume that the previous one is true. I want to show that the next one is also true. So I focus on proving the next statement. The next statement is equality. So in principle, I need to start from the left-hand side, manipulate it a little bit so that I can reach to the right-hand side. Okay, so what I have done here, I have written the left-hand side, and then I realize that from this step to this step, I know based on the assumption of the induction that this equals to this one. Instead of the first few terms, the first k term, I put this expression and I just did some algebra and I reached to the right hand side. Okay, please let me know if you have a conceptual questions that you don't understand, because I will give you many examples so that we can practice and improve our skills. Is there something that you don't understand right here? Okay, so let me solve one more example here. So number 2. Number 2, we are supposed to show that 1 plus 3 plus 5 plus up to 2n minus 1 is equal to n squared. Okay, I want to prove this. So this expression itself, I can call it Pn. So I really don't need to write it down again. Okay, so that is my Pn. The first thing that I need to do is to write this for n equal to 1. So let us see what is the meaning of statement P1. So this is the important thing. So this tells me that if you give me n, I start from 1, I continue, I add 2 units until I reach to 2n minus 1 that you gave to me, okay? Now you are giving n equal to 1 to me. So what is the last number that I can create? 2 times 1 minus 1 is 1. So from the whole expression here, what is left is 1. Okay? And then on the right-hand side, this is a question mark. Instead of n, I put 1. So it becomes 1 to power 2. And this is true, yes? This statement is true. Now I assume that the statement is true for k. This is very simple. Just replace n everywhere with k. So this becomes 1 plus 3 plus 5 up to plus 2k minus 1 is equal to k squared. What is this? Assumed to be true. Okay? Now, you need to be a little bit more careful when you want to write pk plus 1. So what is pk plus 1? It means that you need to replace k with k plus 1. Okay, so let me share my experience with you. On the right-hand side, I don't think you will have a problem. So you will write k plus 1 to power 2. On the right-hand side, make sure that you understand. It means that you remove k and put k plus 1 instead. So it means that you have 2, and then you have minus 1. This empty space is the space for k. I have removed that. I'm supposed to put k plus 1 here. If you write it in this form, it's wrong. I have seen a student sometimes make this mistake, but hopefully you understand that the correct way of writing is this. Okay, so I replace k with k plus 1, but you need to be careful. This here, we really need to put pair of brackets around it. Okay, sorry. Okay, and now you need to simplify this expression. So let me write it down for you here. So it becomes from 1 to 3, 5. You continue until you reach to the k plus first step. So let me write everything here. Yes. Instead of this k, I have replaced k plus 1. But it is clear that when you reach to the k plus first step, the previous step is the kth step. And it is very illuminating if you write the previous one as well. This is very helpful if you write the previous step as well. So now I am assuming that this is true. I don't know if it is true or not. I want to prove that this is also true. Any questions so far in writing this? Okay. And then I would simplify this a little bit before starting. What do I mean here? 1, 3 plus 5 plus up to 2k minus 1. And let me simplify this here. If I multiply 2 here, it becomes 2k plus 2, and then I have a negative 1 there. So this means that this is 2k plus 1 is equal to k plus 1 to power 2. So it means that pk plus 1 is this statement, and I want to prove this based on this assumption. Okay, so what should I do? Again, I want to prove this, so let me start from the left-hand side and try to do some algebra to reach to the right-hand side. So the left-hand side is equal to, so let me repeat the left-hand side. 1 plus 3 plus 5 plus up to 2k minus 1 plus 2k plus 1. Okay, what should I do? I see my assumption. I know that by this assumption, I know that if I add from 1 up to 2k minus 1, the answer is supposed to be k squared. So it means that this expression from here up to here is k squared. Yes? So then it means that this becomes k squared plus 2k plus 1. And then you immediately, hopefully, recognize this pattern. So this becomes immediately k plus 1 to power 2, and that is exactly the right-hand side. You see, I hope that you understand that this is very, very powerful. Yes, it seems like a circular argument. You see, if you want to find a formula for this, you need to be a little bit creative. So you need to be able to find the formula. This is, by the way, arithmetic progression. So in principle, if you remember, you have a formula for Sn in the arithmetic progression, but you need to be a little bit more creative to be able to find that formula. But here, we don't need to be that smart, yes? Somehow, it seems that I am using the same problem to prove the problem itself, yes? So you see, if I want to go to the next step, why it was very powerful? Because I was able to put something instead of this. And that's, of course, it's not trivial at all if I don't have this assumption. So it's very, very powerful tool. Somehow you are able to use the problem itself to prove it. The whole point is to understand this is not kind of a circular argument. And if you doubt it at some stage, please ask me to try. We can discuss about that. Okay, so it's the end of the proof. So it was very simple. So let me give you one more example. Yeah, we have to solve more examples here. So if you don't mind, let me write with blue and then write my solutions with black. Okay. So we want to find a very interesting formula, which is actually very counterintuitive. Yes. We want to see what happens if I add 1 to the 3. So let me start with 1 to power 2 first. 1 to power 2 plus 2 to power 2 plus 3 to power 2 plus up to n to power 2. Okay, now let me talk a little bit about the weakness of mathematical induction. If I ask you to find a closed formula, a formula without these dots, for this, it's not easy at all. Okay, so do you understand? So if I just ask you this question, find a formula for this, mathematical induction is not that helpful because I don't know the second. Mathematical induction works if I have a statement, not expression. This is not a statement, this is an expression. If I have a statement regarding a natural number, then mathematical induction can come to my help and try to prove that. But if I ask you, what is the formula for this? Mathematical induction is actually more or less silent in this case. Unless you start checking it for different values of n and get some numbers for different values of n, then you have a crude guess about a general pattern, and then if that pattern is right, you use mathematical induction to prove that. Sometimes it is possible, but I don't think it's that easy to guess the formula for this by checking different values for it. Okay, now let me just give you the formula. By the way, you cannot use any kind of formulas for arithmetic progression, geometric progression. These are numbers 1, 4, 9, the next one is 25. This sequence is neither a geometric one nor an arithmetic one. So none of the formulas that we studied so far is useful for finding this sum. Finding this sum needs another trick that I don't want to talk about. This is not part of your lesson now. But the formula, if I give you the formula, then it becomes at the level of your lesson to prove the formula. So the sum of these, the sum of the squares of natural numbers has this formula. Yes? Now, mathematical induction is extremely powerful in proving this. Okay? So what should I do? I need to check the validity of this statement for 1. So let me check 1 manually, just by checking. So I start from 1 to power 2, 2 power 2, until I reach to n to power 2. Now n is equal to 1, so it means that as soon as I start, I have to end because I reach to the limit, yes? On the right-hand side, you need to put a question mark. On the right-hand side, instead of n, I put 1. And you need to check if this is true or false. Okay, checking this is very, very simple. So 1 plus 1 is 2. 2 times 1 plus 1 is 3. Yes? 1 times 2 times 3 is 6, divided by 6 is 6. The right-hand side, 1 to power 2 is 1. 6 divided by 6 is 1. 1 to power 2 is 1, so that is true. Now I need to assume that P is true for K. So it means that 1 squared plus 2 squared, 3 squared, up to K squared is equal to K times K plus 1 times 2K plus 1 divided by 6. Yes? And then I need to go to the next step, PK plus 1. So it means that I have to replace K by K plus 1. Okay? So the left-hand side means that I start from 1 to this. Okay, instead of K, I put K plus 1. This is the K plus first step. I told you, you have enough experience that for these problems, it is better to write the previous step, because when you say dot, dot, dot until I reach to the k plus first, it means that the previous one is the kth step, yes? On the right-hand side, you should be a little bit careful. So wherever you see k, you have to replace it by a pair of brackets around k plus 1. So this becomes k plus 1, but I have to put it in pair of brackets. So let us do it in our head, otherwise we have to write a lot. So instead of k, I put k plus 1, that 1 and 1 becomes k plus 2. And here, I have to respect that I need to replace k with k plus 1. Okay? But then I multiplied, it becomes 2k plus 2 plus 1, it becomes 2k plus 3. So this is very important to write the correct form when you replace k with k plus 1. The only thing that you need to respect is that when you replace k, you have to replace it by a pair of brackets around it and write k plus 1. Okay, so again, this part assumed to be true. This is my question mark. Okay? So what we can do now? Again, I start from the left-hand side. So let me repeat it, even though you don't need to repeat the left-hand side over and over again. But okay, this is my left-hand side for this question mark. But I know something. The power of induction comes actually from this point. I don't need to be worried about this hard part. The hard part, by assumption, is this. Okay? So what I need to do is just replace this with that expression. And then what is left for me is just simple algebra. Okay, so you should have an eye on the right-hand side. This is my right-hand side. I have only one fraction with denominator 6. I have two expressions here, so it motivates me to take the common denominator, yes? So if I take the common denominator between this one and that one is 6, so then the left one becomes the same expression, but the right-hand side becomes 6 times k plus 1 to power 2. Okay, then this part depends on your skills that you have actually gathered so far, yes, in Math 2C, Math 3C, to be able to simplify this expression and make sure that expression is equal to that expression. Yes, so for example, here I see that k plus 1 is a common factor here and here, so I can take it out. And this is also needed, yes, because when I look on the right-hand side, I see that I have a common factor k plus 1. So it is reasonable to take that k plus 1 out. Okay, so what is left? K plus 1 is pulled out. K multiplied by this is left. And then I have plus. I pulled one of these k plus 1s out. There were two of them. One of them and this 6 are left. Okay. And then I need to do some algebra, okay? Hopefully at this stage, algebra is actually a minor thing, yes? So I multiplied here. It becomes 2k squared. And then it becomes k. And then I multiply that one. It becomes 6k plus 6. And now I simplify what is here. It's k plus 1. And then I have 2k squared plus 7k plus 6. And I divide it by 6. So that is my expression so far. But it's not that hard to see that this part is exactly this product, yes? So if you want, you can have a check here. If you multiply these two, k times 2k, it becomes 2k squared. K times 3 is 3k. 2 times 2k is 4k. 3k plus 4k is 7k. And 2 times 3 is 6. And that's exactly that expression. So that is completely valid. If I continue, it means that I factorize this. But I don't need to be very skillful in factorization because I already know what I need to get. What I need to do is just check if that's correct or not. Okay? If I ask you to factorize this, you need to know how to factorize this. But you already have the solution here. If you haven't done any mistakes so far, it means that everything should go smoothly, okay? So then it means that, yes, I double check that one. I am not cheating. I realize that that expression is exactly that expression. So this becomes k plus 2, and then I have 2k plus 3 divided by 6. And that's exactly the right-hand side. So that's also a proof for this formula. So you see, as soon as I give you the right-hand side, it was not creative. You don't need to be smart. You just do some very simple algebra to be able to prove that. But if I take the formula away and ask you to find a formula for this expression, you have to be smart to create a better way to do this. By the way, that's also something, if you want to have a challenge, you can think how you can compute this, okay? Any questions so far? Yeah, there are different, so I want to, pardon? Hello?
It seems to be clear.
Yeah, okay, good. So let us, so because this you need to practice a little bit so that you can solve more problems. Okay, but let me do one more problem at least myself here. So the other one is very counterintuitive. So I don't know which was the number. So I forgot. So let me just write it here. So 1 to power 3. So let me write with blue and write with my solutions with black. Okay. So 1 to power 3 plus 2 to power 3 plus 3 to power 3 plus up to n to power 3 is equal to n squared, n plus 1 squared divided by 4. Let me solve this one, and then I ask you, why do you think that this is counterintuitive? Okay, why it should be counterintuitive. Okay, I want to prove this using mathematical induction. Again, I hope that you agree with me. It was not that easy to guess this formula for that sum. Yes? But now we have the formula in its entirety, and that is a formula related to the natural number. So probably the most powerful method is to think about mathematical induction to prove it. Okay, so the first thing that you do is this is your Pn. So I check P1. So the left-hand side becomes 1 to power 3, and the right-hand side becomes 1 to power 2, 1 plus 1 to power 2 divided by 4. So I need to check if that's correct or not. But hopefully you see that the left-hand side is 1, yes? The right-hand side is 1 plus 1, 2, 2 to power 2, 4, 4 divided by 4 is 1, 1 times 1 to power 2 is 1. So it's true. And now I assume that pk is true. I assume that pk is true. pk is very simple. Just simply replace n with k everywhere. Assume to be true, assumption. And then pk plus 1 is what we need to show. So first you need to write it. How should I write it? I replace k with k plus 1. So instead of k, I put k plus 1 in pair of brackets to power 3, but you have enough experience, you know that the previous one is actually this one, and it is useful to write it down. On the right-hand side, instead of k, I put pair of brackets k plus 1. So this becomes k plus 1 to power 2. This becomes k plus 1 in pair of brackets, but plus 1 becomes k plus 2. This is the question mark. Okay, so I start from the right-hand side. The right-hand side is this expression. Okay, so if I ask you what is the hard part in here, you would tell me that from here to here, calculating this part from here to here is the hard part.
Mr. Babak,
Yes? Yes?
isn't that the left-hand side?
Pardon?
Isn't that the left-hand side and not the right-hand side?
I don't understand what you mean.
It says RHS, isn't that short for right-hand side?
Ah, okay, sorry. Thank you.
It was minor fingers.
Yeah, thank you. Left-hand side is equal to that. Yes. And then from here to here is the hard part. But the hard part I don't have any problem with here. That is the miracle of induction. I know by assumption is this expression. The whole thing is to understand that if you want to understand it deeply, you need to really understand that this is not a circular argument. So this becomes k squared, k plus 1 to power 2 divided by 4, and then I have plus k plus 1 to power 3. Yes? But of course, you see that I am supposed to reach here. I am not done yet. At least I see that I have one single fraction. I have two expressions here, so it motivates me to have a common denominator here. The common denominator is 4, and then this will repeat itself. The next one would be multiplied by 4, yes? But again, always you need to keep an eye on what you want to prove. Here I see that I have k plus 1 to power 2. So this motivates me to factor k plus 1 to power 2 from this and that out, yes? Because it's possible. Okay, so let me write up there. So between these two terms, I factor k plus 1 to power 2 out. This k plus 1 to power 2 is completely removed. Only k squared is left. I had 3 of these factors. 2 of them has been removed. 1 factor is left and a factor of 4. So it becomes 4k plus 1. Yes? And then the rest of it is really simple algebra. I don't touch it, this part, because I see I need it. And then I multiply 4 inside, so it becomes 4k plus 4. Divided by 4, but I don't think you need to cheat here because it is very clear that this is k plus 1 to power 2. So this becomes k plus 1 to power 2, k plus 2 to power 2 divided by 4, and that is the right-hand side. Yes, so it means that we were able to prove this equality is right. Okay, now my question is this. Why did I say that this formula is counterintuitive? Can you tell me why?
Because the powers are lower than the powers in the
Pardon? May you speak louder? I cannot increase the
right-hand
volume.
side are lower than the left-hand side.
No, it might be that's also something that you say, but it's more counterintuitive than that. Any comments? Because do you remember the first formula that I proved today was what? Was 1 plus 2 plus 3.
Except one.
Yeah, it was n. It was n times n plus 1 divided by 2, okay? Let me raise both sides to power 2. What happens to the right-hand side? This becomes n squared. This becomes n plus 1 to power 2. This becomes 4. And that is exactly what I was able to show here. So it's counterintuitive, isn't it? Because this becomes equal to 1 to power 3, 2 to power 3, 3 to power 3, up to n to power 3. Yes? So it means that if you have 1 plus 2 plus 3 plus up to n to power 2, usually when you have power 2 here, you expect to have second powers. Of course, the second power is right, but I will have 2 times the first one times the second one, 2 times the first one times the third one, and every combination that I have with the squares, 1 to power 2, 2 to power 2, but at the end of the day, it becomes the third powers, which is very nice, yes? So this is why when I first saw it, I was a little bit surprised. I didn't expect that this formula is true, yes? But now we realize that this is true. We proved this formula by mathematical induction, that's 100% correct. We proved that formula with mathematical induction, 100% correct. Then I found the relation between these two. So this is why this is counterintuitive, because when you want to square a pair of brackets, you need to square all of these factors. So it gives you 1 to power 2, 2 to power 2, 3 to power 2, etc. But it also gives you 2 times the first one times the second one, 2 times the first one times the third one, 2 times the second one times the third one, all the combinations. And then interestingly, all those combinations with these sums of second powers collect into the third powers, the sum of the third powers, which was not that trivial in the beginning. So I would say that this is a nice formula. 1 plus 2 plus 3 plus n to power 2 is the sum of the cubes. Okay, now I want to give another type of examples, including fractions. Everything that I am talking here is in the book, so let us improve our skills there as well, okay? So one example, let us do this. We want to prove this. 1 divided by 1 times 3 plus 1 divided by 3 times 5 plus 1 divided by 5 times 7. And we continue this pattern up to 1 divided by 2n minus 1 times 2n plus 1. We are supposed to show that this is equal to n divided by 2n plus 1. There is nothing special about this. That's more or less you need to be powerful in algebra, in simple algebraic manipulations of expressions, yes? Okay, so what I need to do is to check P1 first. So if I put 1 here, it gives me 2 times 1 minus 1, which gives me 1. And if I put 1 here, it gives me 3. And 1 times 3 is exactly the first step. So it means that as soon as I start, I have to stop as well, because I reach to the limit for n equal to 1. And then I need to ask myself, is it true that I need to replace n with 1? Okay, is it true or not? It is 1 divided by 3, the left-hand side. The right-hand side, 2 times 1 plus 1 is again 3, so it's 1 divided by 3 again, yes? So what can I do? So this means that this is true. So the base of my induction is true. Now I assume that pk is true. It's very easy. Just write everything, copy-paste, except that you replace n with k everywhere. So this is your assumption. So I know that this is true. I assume that this is true. And the next step, you need to be careful a little bit in how you write it down. So I need to replace k with k plus 1 in a pair of brackets everywhere. Okay, so it becomes 1 over 3 plus 1, 3 times 5 plus 1, 5 times 7. It continues. I replace k with k plus 1. So here, this becomes 2 k plus 1 in a pair of brackets minus 1. This one becomes 2 k plus 1 in a pair of brackets plus 1. Okay, but let me write the simplified version here. So this becomes 2 times k is 2k. 2 times 1 is 2 minus 1 is 1. So it becomes 2k plus 1. This becomes 2k. 2 times 1 is 2 plus 1 is 3. The numerator is 1. And now you have experienced that so far that if I write the k plus 1 first step, it's always instructive to write the previous step as well. The previous step is exactly the same expression. And on the right-hand side, I have to do the same. I have to replace with k plus 1 inside the pair of brackets. But pair of brackets is not necessary for the numerator because there is no difference between pair of brackets, k plus 1 or just k plus 1. In the denominator, that is, this expression is exactly this expression. So it becomes 2k plus 3 again. So this is now your question mark. So this is what you can do in a scratch paper. You don't need to write it down. Okay, now I would start from the left-hand side. What I can do, so you don't need to write it that much. So you know that the left-hand side, the left-hand side here is from here to here. By my assumption is this expression. So then I can write it as k divided by 2k plus 1. So you see the left-hand side is from here to here, but from here to here is just this expression. And by assumption, it is k divided by 2k plus 1. And after this, only one term is left. So I have to add it here as well. And then I have to do some algebra to simplify this expression to the right-hand side. Okay, how can I do that? Here I see that I have two fractions involved, but when I look at the right-hand side, I see that there's only one fraction. So this might be motivating to take the common denominator. And the common denominator between this and that is this expression, yes, because it contains itself and it also contains this one. So I take the common denominator 2k plus 1. Then I have 2k plus 3. And then here, this one divided by this one gives me 2k plus 3. I have to multiply it on the numerator here. So this becomes k times 2k plus 3. And then this compared to this one, if I divide with this 1 times 1 is just 1. So I need to add 1 to it. Okay? And what I do now is to try to simplify. And if you have a little bit of experience, you know that you shouldn't touch the denominator because the denominator is already in the factorized form. It's a product. But this is not still in factorized form. If I ask you read it, you would say this is the sum between this and that. So it's not factorized form, because factorized form you should say it's a product between this and that. Okay, so let us try to see if I can simplify this a little bit. So I will not touch the denominator as I told you. So it is 2k plus 1 multiplied by 2k plus 3. And I multiply here, it becomes 2k squared plus 3k plus 1. I don't know if you can guess the factorized form of this. It's not that hard to guess, by the way. So if I want to write it as a factorized form, so let us guess what would be the factorized form. Of course, if you don't want to guess, I can give you the instructions, but it is better to guess because instructions is a little bit more tedious. So here, I would write a 2k here and a k here, and try to adjust these numbers in a way that when I multiply, it gives me here. But of course, I see that this product also should be 1. So the first rough guess is that this is 1. This is also 1, yes. But then you need to make sure that this is indeed correct by multiplying it back in your head. So 2k times k is 2k squared, that's good. 2k times 1 is 2k, 1 times k is k, 2k plus k is 3k, that's also good. And then 1 times 1 is also that. So that was quite good. And now this is in factorized form. So 2k plus 1 and 2k plus 1 are common factors. So I can, yes? Yes?
There's a sneaky way also. If you look at the denominator, you see that there's
yeah, but this depends that you trust yourself up to this point exactly. Yeah, that's up to you. This at this step, that's called a little bit of cheating, but that's also okay for me here, because at least you understand what's going on. Okay, so this one and that one are simplified, and that what is left is k plus 1 divided by 2k plus 3. And then what is this one? That's exactly the right-hand side. Okay? Okay, so the mathematical induction, the lesson is finished, but I want to teach more type of problems that we can use mathematical induction to prove it. As a rule of thumb, whenever you have a statement regarding a natural number, one powerful tool in your hand to be able to prove that statement is mathematical induction, okay? But it is better to see different types of problems so that you have enough experience. Okay, so we talked about 2 types of them here. So I could say 1 type, because here we have these formulas with dots. We want to prove equalities, algebraic equations, algebraic identities. So the one that I started with doesn't involve any fractions, but this one involves fractions. I think I will stop teaching here, but I want to write some problem here for you on the board so that you can try to work on this yourself, okay? Okay, so let me write some problems here if you want to continue yourself. So 1 to power 2 plus 3 to power 2 plus, no, sorry. 1 to power, yeah, that was right. 3 to power 2 plus 5 to power 2 plus up to 2n minus 1 to power 2 is equal to 4n cubed minus n divided by 3. Yes? So that is one, you can work on it if you like. Another one is 1 times 3 plus 2 times 3 to power 2 plus 3 times 3 to power 3, and then plus up to n times 3 to power n is equal to 3/4 of this expression. That's also good to work on. And the other one is 5 divided by 1 times 2 times 3 plus 6 times 2 times 3 times 4, 7 over 3 times 4 times 5, and then you continue n plus 4 divided by n times n plus 1, n plus 2, and on the right hand side you will have n times 3n plus 7 divided by 2 times n plus 1, n plus 2. Yes. So if you can solve these 3 problems on your own, it means that you are on the safe side. Everything that I talked about today, it means that you have already learned that. Okay. So I will end this live stream now, but I will be on Zoom until the lesson ends. And if you have any questions, hopefully I can answer you through Zoom.